All right, well, welcome folks to our second session. What I always like to do when I lecture is I just like to give an overview of the key points from last lecture after they've had a time to stew in our brains a little bit. So I'll do that, and then I'll use that as the launching off point for today's lecture. So last time, we began really the introduction with a description of the ab initio approach and the idea that we'd all like to live Empedocles' dream. And that's really what this course is designed to do, for you to be able to do that in a very real way and code things up for yourself from scratch. That's our code philosophy here. And that relates to one little change I'm going to have to make in the course sequence already, because I'm really want us all really to have the chance to really live this dream, and you're not doing it yourself if you're not building up your own code and not understanding everything that goes into it. And we've had a lot of nice discussions in the last lecture, and I realized my plan for what I'd cover in these two lectures was a little overambitious, so that if I keep that assignment due on Tuesday, there's a certain 10-minute riff I won't be able to finish today. And you really need to know what's in that 10-minute riff to really understand what's going on while you're doing the coding. And I want you really to understand everything that's going on while you code if we're really going to live out this dream. So that first assignment then is going to be due 1 week later on Tuesday of the following week. So, and you probably won't have enough material until just the beginning, the first 10 minutes of next Wednesday's lecture to get started on. So you can give it a shot, but you definitely want to start it after next Wednesday's lecture, because then the assignments might stack up a little bit if we don't get a good early start on them. So that's a little announcement there. After discussing that, I showed you how we were going to carry this out by working within density functional theory, and I wrote down the basic ideas behind density functional theory. The main thing I wanted to emphasize there was that everything that goes into it, I think, is pretty intuitive and pretty straightforward. It's pretty much what you'd write down after your first semester of quantum mechanics. The one thing you might miss would be that, well, there's this little extra correction term here, which can make this all an exact theory. The problem is we don't know exactly what the function should be, but there is this very nice approximation to it known as the local density approximation. I've written that very simple form for you here, and that's good to predict most materials' properties to within a few percent. And I then showed you examples of this thing working in practice, and indeed, in fact, that's about how accurate the theory is. So my claim is, if you will, scientifically justified. I can't formally go and justify without a couple of lectures like we did last year about why we should expect that level of accuracy from this theory. But if you think about it from a scientific point of view, why do we believe the many-body Schrödinger equation anyway? Well, basically because it lines up with all the experiments we've done so far, and we have some faith then it might work in new circumstances. Well, same kind of justification I could give for you here, right? It's worked in a lot of circumstances so far, so we have pretty good faith it's going to continue to work. And there's also formal reasons, but we don't have time to go into those. Then I emphasized to you that we're going to begin by pulling out one little subpart of this problem, which is solving Poisson's equation, as our first run-through for our approach to computational problems. So we're going to just focus on a simpler aspect of the problem. And then I was using that as a foil to teach you good computational practice, where the first thing we did, and I've already included those up here, is it's always important to make as many, or solve the problem as much as possible analytically first, before you go just trying to put it on the computer. We went through and chose appropriate system of units and simplified the number of double integrals in here. We've already carried that out by the time we've gotten to this point. Secondly, we had to decide upon our computational representation, and for Poisson's equation we have these two fields, the potential and the density, and we decided that in 3 dimensions at least it would be good to expand these things in a basis set, so then our computational representation, rather than trying to store an object which exists on an uncountably infinite number of points, and then you couldn't possibly store the data, would be to store it in a finite set of coefficients, the expansion coefficients in a basis set expansion. And then those expansion coefficients, those become our computational representation, and we can gather them into some vector. The expansion coefficients always put a hat on top of them, so when I gather them into a vector, I'll be calling them phi vector hat. And similarly, there's an analogous set of expansion coefficients for the density. The alternate representation, which we'll use a little bit today, would be to just look at it at a finite set of points in space. And those, again, could then just become a finite set of sample values of our function, which, again, we could gather into a vector. And then finally, I emphasize this expressive software approach, and today we're going to see how close I can kind of come to that ideal. The ideal being where we could fine-tune our natural language just a little bit so that we can think in a language which then also could be transcribed directly into our software. Kind of like the experience you have like deriving equations in LaTeX. So we're going to try to do that today for Poisson's equation, and then you guys can be the judge as to how close we get to that, what kind of a job I'm doing with that. So that's pretty much what we had covered, and so now we're going to jump right on in. Now some of the analysis I'm going to do on the blackboard here is, in some sense, kind of straightforward and trivial, but in the other sense, a lot of what I'm doing today is introducing notation and concepts and things that are going to carry us out in good stead, and changing our perspective on some things we've probably written down many times before. So bear with me as I go ahead and do that. And along those lines, one of the notations I want to introduce and to emphasize to you is that within this course, by a vector, I always mean a column vector. I'm very, if you will, column vector centric, maybe a little biased against row vectors, but at least this way we can always keep the computational representation straight. So every vector in this course will be a column vector. If I need a row vector, I'll write the transpose of a column vector. I always want everything here in column vectors. That's just my personal style, because I'm getting too old to keep track of who's a column and who's a row. So all the vectors will be column vectors. And now we want to jump on in and try to solve Poisson's equation here. Here's our agreed upon computational representation. And the statement of the problem basically is, given the density, our job then is to solve and find the corresponding potential. So the first thing we'd want to do is to take our computational representation and put it into the equation we're trying to solve. So we'll just have del squared, sum over the basis functions, expansion coefficients, basis functions should give me minus 4 pi, sum of expansion coefficients times the basis functions representing the density. And then the problem we have here immediately is you'll notice that this thing, much like our continuous functions, this equation, as written, holds at an uncountably infinite number of points. So there's an uncountably infinite number of conditions, but I only have a finite number of coefficients that I can adjust, so clearly I'm not going to be able to solve this problem, as stated, as an algebraic or computational problem. I need some way to boil down this condition to a number of conditions equal to the number of coefficients which I have, or in other words, equal to the number of basis functions. And the standard approach for doing that is the Galerkin method, or one standard approach. And in the Galerkin method, what you do is you take both sides of your equation and you integrate them against the complex conjugates of all of your basis functions. And that clearly then will give you as many conditions as basis functions. So we'll go ahead and discretize the problem that way. And as I do that, I'm just going to proceed and do it, and recall, of course, because of the distributive and commutative and associative properties of addition and multiplication, when I do something like this, any string of symbols can be rearranged at will any way I wish, so long as any indexed object appears to the right of the summation corresponding to the index. So as I write this, I'm going to do some rearrangement. Working on the left-hand side of my equation, I'm going to start by moving the summation all the way to the left. So I'll have the sum over alpha, then I'll deal with my integration, d cubed r, and then I'll have d beta star r. Then I have what pieces here. I'll deal with the del squared because it refers to r, del squared d alpha r. D alpha r. That's my integral, and then all that's left on this side, I believe, is the expansion coefficient phi hat alpha. Looking then on the right-hand side, same kind of a thing. There's a minus 4 pi. And now I'll do my rearranging game. I'm integrating against my basis functions. So I'm going to have I'll pull the summation out, and then I'll have integral b cubed r b beta star r b alpha r as an integral multiplying the expansion coefficients and have alpha like that. Now let's take a look at what we have and how we might fine-tune our perspective on it a little bit. This set of integrals here is just some set of numbers that is defined by my basis, so I may as well give it a name. It's clearly just the matrix elements within my basis of the Laplacian operator, so I might as well call them L, and they carry these two indices, beta alpha, and that will constitute one definition for me, and I'll put a little box around my definition. Over here, same kind of thing. These are the overlaps between my basis functions. So I should give that some kind of a name. I'll call it O for overlap, and again it carries two indices, beta and alpha. And that will constitute the second definition. So any questions at this stage, or comments or commentary? All right, good. Now, I do want to emphasize here at this point that, and also a frequent question I get as well, if the basis is orthonormal, then this is the identity, right? But I do not want to restrict myself right now to any particular basis. Plane wave basis, sure, we can arrange for that to be the identity. On the other hand, there are many other very good bases out there we might want to use one day. We might want to use, chemists are fond of Gaussian functions, right? Finite elements are an interesting other choice one could use for these equations, or I had done some research on using wavelet functions to kind of resolve things down near the nucleus. So I really don't want to commit myself at this point to any particular form of basis. What I really want to do is keep my language here as general as possible. In a way, what I want to construct here is the analogy for density functional theory, what Dirac notation is for traditional quantum mechanics. I would like a notation which is completely basis set independent of the underlying representation, something which is intuitive to think in terms of, because I'm looking for this kind of expressive software, some slightly new natural language. And I would like it also to be, how should I put it, manipulatable analytically, very much like the Dirac notation is. So we can think our physics, hopefully, is going to look like our expressions. So in that regard, I want to bury or subsume all of my basis set details into these mathematical objects. From a computational point of view, that's not a bad idea either, if you think about it. What this is going to do is it's going to modularize our computational structure, where the physics, which will be written down in terms of L and O, may appear in, say, the top levels of my code, where I might be changing my physics around and trying out new physics. But then, if I want to switch basis set or something, right, I don't have to worry about that if I'm going to write, I don't have to write a new code for a new basis set. I can keep the physics all on one level and keep that the same, and then, yeah, sure, later on, what these elements are might change as I try out a new basis, but I'll only be changing the specifically relevant pieces of my code. It helps keep things nice and modular. All right, well, with that said then, let's look a little more at our expression. And you can see clearly what's happening here is that this is performing an operation on my computational representation for phi, which is nothing other than a linear transformation. In fact, things are written out perfectly here as a standard matrix vector multiply. So this here looks just like I were taking the matrix L. So, and for matrices in this course, I'll represent them always as boldface. And Blackboard boldface, best I can do is kind of make a double line there. So that's L matrix multiplying the vector phi vector hat. It's a square matrix times a column vector. And what that's giving me on the other side of the equation is similarly just minus 4 pi O gathered into a matrix. So make it Blackboard boldface times n vector. And that's my representation for Poisson's equation. And what I'd like to argue for is the perspective that, well, that's pretty much the way we think of Poisson's equation, isn't it? It's some linear operator here on our physical field, and it just turns into a linear operator on our corresponding computational representation. And then the right-hand side, and that's the Laplacian. I'm using an L. That's reminiscent, sure. And the right-hand side, I've got my minus 4 pi times my representation of my density, just like I have here. The only slight difference, and after a while will become intuitive to you, and you'll know exactly where to put these, is the appearance of this little extra O, the slight cost I'm paying for keeping this a completely general representation and not assuming orthonormality within my basis. But after a while, you should be able to just write this down. This is clearly Poisson's equation. Okay. Now, our goal, though, of course, is to solve the Poisson equation problem, namely, given the density, find the potential. Well, it's easy enough for me to solve this equation, right? Clearly, phi vector hat is going to be, I'm going to have to invert the Laplacian on the right-hand side of the equation. Now, that one issue, though, to keep in mind is that, well, yeah, that's fine, except usually when we're asked for the potential phi, we are not asked for it in a, for its expansion coefficients in some basis that we find convenient. Oftentimes, we're just asked for the values of the potential at some set of points in space. So we need to be able to convert between those two representations. Well, that's fairly straightforward because actually, after all, we just have this expansion expression right here. So if I want to know the values of the potential at any point, I just, of course, sum up the basis expansion. And if I want to know these on some collection of points, Rp, well, this would then be just the transformation which I would use. And these actually constitute our other representation, a collection of sample values for phi. And we can get that collection of values from what is evidently yet another linear transformation on our computational representation. The kernel for the representation, then, are these values of the basis functions. And if I want to maintain my perspective of keeping these guys as column vectors, and I want this to look like a standard matrix vector multiply, this 2-indexed object should appear before the 1-indexed object. And when it does, the alpha should appear as the second index. So I'm going to index this thing in maybe a slightly counterintuitive way in my definition that the index should carry p first and alpha second. And I need some name for this matrix, if you will. And I apologize somewhat, but for historical reasons, I like to call that I. And just as a historical footnote, the reason is that at the time, I noticed that there was a lot of generality in all these density functional codes I had written for different bases, and realized that I kept doing the same thing over and over again. The particular basis set I was working with were this generalization of wavelets we had been working on and have developed, which have certain interpolating properties, so they carry the name I. So, but anyway, the I is just the name that I give to them. And then you can see here, you know, if I write this out, it's sum on alpha. In this order with this definition, it then follows the standard matrix column vector multiply motif. And so this, as a vector equation, would say the vector of sample values for phi can be obtained by taking the matrix of basis function values, which I call I, times my expansion coefficients for phi. That's just some linear map. Good. Okay, so we're getting there. Once we can get these phi hats, we can get the phi's, which are our final target. The other thing, of course, is that usually we're not given the expansion coefficients for n in the basis set that we find convenient. Usually we're given values of the density at some set of points in space. So I have to do some other conversion. I have to figure out how to go from n, I have to figure out how to get n hat from somehow n. The sample values for the density, somehow there should be some map that will give me the expansion coefficients. So let's see how well our notation is feeling a little bit intuitive. Any suggestions how we're going to go about finding that?
It's I inverse.
Right, it looks just like I inverse, right? Evidently, if you follow the logic here, it doesn't matter that I'm talking about phi. The general rule seems to be If I want sample values, I apply I to the expansion coefficients. So the sample values for the density will be I times the corresponding vector of expansion coefficients. And then if I want to solve for these, given the sample values, I should apply the inverse of I. Now, for reasons which I'll specify in just a moment, I'd like to call the inverse of I J. That's I inverse. So then there's just a different transform, if you will, called J that will take us from sample values to expansion coefficients. The reason for doing that is, again, a matter of generality, which won't really impact us too much in this course, but it's worth keeping in mind. And that is that oftentimes your sample values representation will have more points in it than your expansion coefficients, right? If you found a good basis, it's going to work that way. As a consequence, this matrix I is not a square matrix, and you can't invert it. On the other hand, what you would do in that case is you would try to find some least squares fitting procedure to best match the values of those samples. That will be, in general, some kind of a linear map, and I represent that map by J. In our particular case, J, in fact, will just be taken to be defined as the inverse of I. But at least this way we maintain generality. Good. So now I've got all of the ingredients I need. I've got this relation, and Poisson's equation as solution to write down my final solution to Poisson's equation. So if I wanted phi, and I want to show you how, again, this is hopefully becoming fairly intuitive language. It's going to take a little practice. You know, this is the first time you're seeing it. But here's how I would write down this expression. I would say, okay, I know I start with the sample values of the density. Right? That's what I'm given. And I've got to figure out how to get the sample values for the potential. So what am I going to do? Well, first, I have to get into my computational representation. So I'm going to apply J to get my expansion coefficients. And those expansion coefficients, then, are what appear on the right-hand side of Poisson's equation. So there's going to be a minus 4 pi. And as we had mentioned, there's a slight cost for your non-orthonormal basis, which is, there's that matrix O. That then constitutes the right-hand side of my representation for Poisson's equation. I have to invert the Laplacian to get back to the potential. There's going to be an L inverse. We'll apply to this. That will give me my computational representation for phi, namely the expansion coefficients, which then have to be transformed forwardly with I back to give me my sample values. And that would be the solution to Poisson's equation in just one line of code in this language. So I'm hoping, you'll see with a little bit of practice, you'll get the hang of this. And if you want to check me, you can just, back substitute each of these expressions that I was writing, and clearly you'll have it. All right, so any questions at this stage? Okay, so this I hope has achieved, my first goal for this language is that it should be somewhat intuitive. My second goal should be that it should be manipulatable easily, to do formal manipulations on it. That will become more clear in later lectures. There are not actually too many manipulations to do here, but I think you can see this is all, linear algebra with matrices and vectors. We know how to manipulate those, so I can do derivations with this kind of a thing. If I wanted, the partial derivative of phi with respect to n, well, I just know it's this product of matrices, for instance, right? We've done enough linear algebra, we know that. So we'll be able to manipulate it formally. And the final goal was that this should be transcribable, remember, from my derivation on the paper doing my physics in a slightly retuned language into computer software. But I can write this down in any number of languages just as it appears, I argue. I could write this in C++ or MATLAB, which is the same as the Octave language, which is what we'll be using in this course, or Python also. And if I were to write this in one of those languages, I would write it this way. I would just say phi equals, there's some I, which is some linear transformation, which will apply to another linear transformation, L inverse, which would apply to minus 4 pi times, no. Can't do that on the keyboard, sorry. 4 times pi times, that's not so bad. We can live with that. Times O, right, which is applied to J. which is a linear transformation on n. And okay, 1, 2, 3, 4. And to make it official Octave or C++ code, I need a semicolon. But that's not true. You look at this, I argue, your brain parses this. In fact, literally speaking, forgetting about the computer language thing, the meaning of parentheses in the algebraic language we've learned all our lives is multiplication. So this really is literally the same thing as this. The only kind of subtlety I would say here, and this has to do with a coding practice, why do I write this? See if maybe someone can guess. Why would I rather write the expression this way than as I times LM times, blah, blah, blah. Why do I prefer this representation over that? From a practical point of view, what do you think? Sorry.
Then you only have to define what the function does on a vector and not what it does on a matrix.
Exactly, right? To carry out this operation, you would have to build these matrices, right? And then multiply a lot of big matrix times vector multiplication. Oftentimes, these matrices have special structures that make that operation much easier to carry out computation. Easy, for instance. If we are dealing with plane waves, then O will be diagonal. Depends how we normalize things, right? O will be diagonal. And if O is diagonal, if I want to apply it to a vector, the easiest way is just to go down the vector and multiply by the corresponding components. Right? That's much more efficient than building a giant matrix with a whole bunch of zeros and doing some BLAS3 giant matrix multiply. Similarly, for plane waves, as we'll see, I and j are going to turn into the fast Fourier transform. And applying the fast Fourier transform to a vector is much more efficient than building up that matrix kernel and then multiplying it out. So the use of these parentheses is more a computational optimization, but I would like to argue that your mind will parse this in just the same way as it parses that. And once this becomes intuitive, so will this be. And our physics code will be quite nice and will correspond to what we're thinking. At least that's the goal. Questions? Comments? At this point. Sir?
What about cases where L is such that L inverse is not easily computable? You want to do iterative solution or something like that?
Right. Exactly. So the question is, if L is a matrix which we can't invert analytically or directly, right? How are we going to apply, and that's again comes into this idea of writing these as operators, how am I going to multiply by L inverse? Well, I will end up writing a routine which does some iterative solve. And there are plenty of those out there, and then I'll encapsulate that routine. Fair. Very good. Other questions? Okay, so that's my single line of code. Now, of course, you can see what's going to happen is that, well, now we're tasked with the job of implementing these operators. L inverse, we just got a question on that, and all the other corresponding operators. What's nice is it's almost now a mechanical turning of the crank. Once we write down what our basis set is and decide upon it, all of these objects then are defined. We have to go ahead and calculate them, which we are about to do, and then figure out what are the best ways to actually implement the corresponding operators. One nice thing, though, I want to emphasize again in terms of coding practice is that on one level, we have our physics. On the other level, we are writing these very well-defined mathematical operations. And I can tell you from long experience, right, you'll have much better luck talking like a computer scientist, say, or a numerical analyst. You'll have a much better job talking them into helping you write highly optimized operators that have these crisply defined mathematical definitions than showing him your physics code where all these things occur implicitly in a bunch of different subroutines and asking him, can you please help me optimize my code? That never works. But the other one does work. And also, when you're running a research group, as you will one day, right, sometimes you'll find students who have a real knack for and interest in actually tweaking up well-defined mathematical operations. Some other students really don't want to ever have to deal with that and just want to deal on the top physics level. But this way, the two can work in concert quite nicely. So that's the sales pitch on that perspective. So that's kind of what the expressive software approach would look like in practice. So now we're going to go ahead with the rest of the practice and deal with a specific basis, if there are no other questions. All right. Basis, plane wave basis. So plane wave basis. And this is what you'll be implementing on the assignment. This is just a not as fancy word for spectral methods. And as we'll see, the advantage in spectral methods is that, in particular, the Laplacian has a very simple inverse in this particular basis. That's one of the big advantages. The other is that the transforms exist as very highly efficient routines and standardized packages. Okay, so what's our basis set going to be? As I had mentioned, the solution of Poisson's equation requires that your basis be commensurate with your boundary conditions. In this case, we are dealing with periodic boundary conditions. As I had stressed last lecture, what's nice about these is you can do solids, but also you can do molecules if you're willing to repeat them in some big, giant box. And within periodic boundary conditions, we have to specify, precisely what we mean, and what we mean by that is that the function, whatever it is that we're representing, and hence also all of our basis functions, should be the same if you evaluate it displaced by a certain distance. Right? Function a certain value here, then it repeats over here, and it repeats over here. In 3 dimensions. I'm just curious, how many people here are from the physics department? Almost everybody, but not everybody. Okay. So not everybody, eats, drinks, and dreams about periodic boundary conditions. So in 3 dimensions, there are 3 different repeat distances, if you will. Actually, 3 different repeat vectors, known as the lattice vectors, and they don't have to be orthonormal. They just have to be 3 different vectors that span the space. So I'll try to draw such a set. This I call R0, R1, maybe I'll make R2 big and tall, like this. And then our repeat unit, our basic unit of space then, is some parallelepiped. Let's see if I can get it to look kind of like the top is like the bottom. There's no problems with that. That's not too bad. Yeah, like that. So this interior space then becomes my unit cell. That's repeated periodically throughout space. That's often called omega. Like that. So those are my periodic boundary conditions. And the basis functions, a set of basis functions that are nice and periodic in those, B alpha of R for us, will be just plane waves. And as I change alpha, all I change about the plane wave is the wave vector. And notice I'm not really worrying too much about the normalization of these. I don't have to make them orthonormal. I don't have to make them actually anything, right? Because my factor of O there will compensate for anything. So I can be pretty simplistic about picking my basis functions. So that's going to be my basis functions. And now my job is to go in and turn the crank and evaluate all these various definitions to build up the various operators. So I'll start with the simplest one, which is the overlap operator. O sub, how is it defined? Beta alpha is the integral b beta star b alpha d cubed r, which in this case would be integral e to the minus I g beta dot r times e to the I g alpha dot r d cubed r. And who can tell me what this will give? What do I get if alpha is not beta? 0, right? Basically, if alpha is not beta, these complex exponents combine, and I've got some wavy looking thing, right? And if I pick the right g alphas, which we will momentarily, then when I've got a wavy thing integrated across my box, I get nothing. The other alternative would be that beta equals alpha. In that case, I'm just integrating the value 1. So this is going to give me a Kronecker delta. and then an integral of 1 over some volume, and I didn't specify, and it doesn't matter as long as you're consistent in all of your definitions. Another nice aspect of the framework we have. Usually you integrate over your repeat unit. So this will be the volume I'm integrating over. So that will just give me then Kronecker delta times the volume of my unit cell. And we should actually be able to write the volume of that cell in terms of these lattice vectors. And that would be what in terms of those?
Box product.
Say what?
Box product of the vectors.
Box product. Oh, I haven't never heard of that one. But yeah, triple product, box product, however you want to call it. Right? Also, another way to write that, and that's what will be convenient for us, is to recognize that this is the determinant of a nice matrix that I like to define. And that matrix is the matrix where you put the column vector, right? We're always column vectors in this course, R0 first. And then next to it, you put the column vector R1. I'll put these vectors to emphasize they are my column vectors. Then next to that, column vector R2. Take that determinant. Another way to write this, and here I'm introducing a little octave notation, which we'll be using throughout the course, is to, if you want to put things next to each other horizontally, octave uses commas for that. So if these are column vectors, and you write this expression, this thing will correspond to this 3x3 matrix. And I like to call that matrix R, and it's a boldface R, of course, because I boldface all my matrices. So a little bit of octave notation for you. So note, comma in MATLAB or Octave is composition by horizontal stacking. Oh. And by the way, semicolon stacks vertically. So if I had put in, if I had put semicolons here, right, I would end up with R0 as a column on top of R1 as a column on top of R2 as a column. I would have made some, 9 long column vector. But I put commas to make a nice 3x3 matrix. So another way I can write this would be, of course, to say, well, as a matrix, O is just the identity matrix times this volume. So 1, boldface 1 is how I write the identity matrix, times determinant of R, if you want in matrix language. And if you want to implement it as an operator, O applied to an input vector should just give the result of simple scalar det R times the input vector. This is how we would implement it. You would never implement it by actually making a big identity matrix involved. Good. So any questions on O? Okay, work our way down to L. Next. I hope you can see this is pretty, straightforward and mechanical the way we define things now. So here's my definition of L. Just the matrix elements of the Laplacian. So L beta alpha is integral d cubed R b beta star del squared b alpha, which turns out to be d cubed R e to the minus I g beta dot R del squared e to the I g alpha dot R. One of the nice things here is that, well, every time I take a Laplacian of the complex exponential, I just pull out a factor of I g alpha. And I'm doing that twice, so I'll get just minus the magnitude of g alpha squared times my original basis function back again. This is just a constant, and now I'm just doing my overlap integral. And we've already gone through all of that. So I just get minus magnitude g alpha squared times the corresponding overlap integral. And the overlap integrals were all Kronecker delta alpha beta times the determinant of r. Like so. Good. Any questions? Straightforward. All right. Hopefully. And then as a matrix, here we learn some more important notation that will keep us in good stead. Some of this notation seems like overkill in this lecture, but in the next lecture it will become more and more important. As a matrix, L is equal to, okay, there's a minus determinant of R. Fine. Now, what does this look like as a matrix? What is that? Say again? Someone said it.
Determinant g beta square of the diagonal.
Right, and this will just be these square g's along the diagonal of a matrix. And the way we denote that is to say, I'm going to make a diagonal matrix, so there's out of a column vector. So there's an operator called capital diag, which will take a column vector and turn it into a diagonal matrix by dispersing the diagonal elements, by dispersing the vector elements along the diagonal of the matrix. And so that diag has to apply to a column vector of these g alphas. So I can make that vector by saying, okay, I'll take g0 squared. And I want to make this a column vector. So I compose by vertical composition, semicolon, put g1 down below it, g1 squared, etc. Where now I've defined that diag element, I'm going to need this definition of the transform coming up, so I don't want to disturb that one down there. So there are two complementary operations that we are going to be using. One is diag, which takes a vector input, right, and it gives a matrix. And how it works is basically the elements of that vector, right, get turned into a diagonal matrix where those same elements are on the diagonal and zeros are placed everywhere else. And I write it as a boldface because the output is a matrix. There's a complementary operation, lowercase diag, which applies to a matrix. So I'd start with a matrix. And then what I will get out is a vector. And what this thing is designed to do is it takes a full matrix, not a diagonal matrix. Right? There's all kinds of elements everywhere. But this operation takes the elements along the diagonal, whatever they are, and arranges them into the same exact elements. It arranges them into a column vector. Just a copy of this thing, but turn 45 degrees, basically. Okay, so sort of as a test here, see how if we're parsing these yet. What would I get if I took, let's see here, diag of the diag of a vector? Okay, let's see. So if I have a vector and I do the capital diag of that, what do I get? A vector or a matrix? Matrix. And what's on the diagonal of that matrix? The vector, right? And then if I take diag of that, the little vector diag, what I do is, here I'll do this step by step. So I start with my vector, right, like this. Diag of it makes it into a matrix where those elements from the vector are dispersed along the diagonal of this matrix, and the rest of the components are 0. That's what the diag did. Then the little diag looks at my matrix, looks at what's on the diagonal, and turns those into a column vector, like that. So, what have I ended up with? Say again louder. I thought I heard someone say. Raise your hand if you know the answer to this question. I won't pick them. All right, most of you guys know. Okay. So, what you get is the vector back again, right? Because it got put on to the diagonal of the matrix, then it got pulled back off the diagonal matrix. Okay, fine. So that's V. What if I do it the other way? What if I do diag of the diag, vector diag, of a matrix again? Do I get the matrix? No, I don't get the matrix. What do I get?
Diagonal elements of the matrix.
I get, right, exactly. I get my if my original matrix looked like this, with a whole bunch of numbers in it, and certain ones along the diagonal, by the time I've done this, what I'm going to end up with is all the ones off the diagonal will be zeroed out, but I will preserve the ones that are on the diagonal, because this guy stored those diagonal elements as a vector, which got replaced along the diagonal elements of the matrix. So those are those two operators. Their use will become more, why we would want such operators, become a little more evident later. Now, Octave / MATLAB language has this operator. Uses actually lowercase diag for both operators. Okay? But it's overloaded, so it knows if it's given a matrix, it'll make a column vector for you. And if you give it a column vector, it'll make a matrix for you. And you just maybe, because I see some people are getting, some people aren't, you just have to try it out in Octave a couple times. It'll become, obvious for you what it does. I, though, need these, as we'll see. We're going to need these operators later. We're going to depend on them pretty heavily. So I like to distinguish them this way, so at least we know what we're getting and what we should be expecting as input. More questions on the diag? All right. People getting, maybe they need a break or something. Okay, so anyway, what would I do? I computed L for you. Is this nice diagonal thing? To multiply by L, again, would be fairly straightforward. What you would do is you would take your input, just fits, L on an input vector V, right? Or on a set of input values V alpha, is just going to give me by the definition minus the determinant of R, right? Times then the corresponding G vector squared times V alpha back again. Just go down your list, you multiply by your G's. You're just multiplying by a diagonal matrix. That's how you would implement it, and that's much faster than making a matrix and doing the multiplication. Okay. So that's the L operator. Okay, good. We're cruising right along. What's next? I. I is next. Now to specify I, you see, we need to know not only our basis, but what our sample points are going to be. And for these kinds of boundary conditions, there's one, sort of obvious choice, I think. Well, there are many choices, but there's one natural choice, I should say. And that natural choice actually will give us a very nice result for the values of I. So any thoughts on what that natural choice might be? Where should I distribute in my volume here my sample points? How should I specify? choose RP. Maybe try to describe in words where they should go. Clearly, random is probably not the best possible choice. Well, Monte Carlo, maybe it is, but this isn't Monte Carlo. Got a box. What if I just had a rectangular box? Where would I put the points?
In a grid?
In a grid, right? A nice regular grid. I chop it up some number of points in each direction. So maybe I would do the same thing here. I chop this guy up into S0, S for size, right? S0 points along that vector. S1 points along this vector. You know, because some of these vectors might be longer, like R2 is in my diagram, I may want more points along it. So I should allow for different numbers of points along each one. Very good. And so then what I should do to fill in this grid is I should just go, you know, the corresponding distance along R0, the corresponding distance along R1, and the corresponding distance along R2 to specify my point. Right? And that way I will fill in this box nice and uniform. The grid may not be, you know, square grid points, but you know, it will at least be a regular pattern, and all of our algebra here is going to take care of any problems you might worry about if they're square boxes or not square boxes. It doesn't matter. The framework takes care of all that for us. Okay, so what I'm saying then is that these guys would then, the best way to do this is as, you know, a fraction of vector R0 plus a fraction of vector R1 plus a fraction of vector R2. So I'm going to have some integer, I guess, m0 over s0, where m0 will run between 0 and s0. That will give me fractions between 0 and 1. I'm going to have that amount of r0 plus a similar fractional amount of vector r1 plus another similar vector amount along r2. Like that. That will make a nice little regular grid there. Right? You know, similarly, m1 is between 0 and s1, and m2 between 0 and s2, like so. Good. Now, I guess as long as we're at this, we may as well continue compactifying this into a nice compact matrix language. The more I do this, by the way, every time I derive a final matrix expression now, I'm giving you the code that you need for your assignment. So we're deriving exactly the code we'll be using. Okay, so let's calculate this guy. Well, let's try to get this into a matrix language. I've got some linear combination of these three vectors R. Notice that if I stack them horizontally like so, and multiply this by a column vector, which is m0 over s0, m1 over s1, m2 over s2, that gives me, right, when I multiply this element times this amount times this amount times this is my first answer. I will build up exactly these vector positions. Good. And now this vector, I could also construct, oh, and isn't this nice, right? This is my lattice vector matrix R. This quantity then can be constructed from this column vector m0, m1, m2. And what do I need to multiply it by in here to get these s's like that? What kind of matrix? How would I arrange these s's in a matrix so that I would get m0 over s0, m1 over s1, m2 over s2?
But diagonal matrix is 1 over 0, 1 over 0.
Very good, right? You would make a diagonal matrix out of these s's and multiply it by that vector. So that would be big diag of s, where s vector, one of my favorite column vector type things, right? Which is s0, s1, s2 made into a vector. And as he said, of course, I better not forget, I should invert it like that. And as long as I'm naming vectors here and making better notation, those m's, if I want, in a column, that would be my vector m. Okay. So that then gives me my sample points. RP, right? It's a column vector. Is lattice matrix inverse of the diagonal of the size matrix times a little triplet there of integers. And each triplet, of course, a different triplet will give me each different point. Now,
You left out your inverse.
oh, thank you. Now, there's another object I like to build. Sometimes it's nice to make all of these points in space, if you want to evaluate a function on them, for instance. So I like to make a matrix R that contains all of my little vectors, all of my position vectors, all my sample points. The way I like to arrange it, and sometimes I wonder why, this is the way I like to do it, is it's more natural to have a list where the first vector goes across the first row, and the second vector across the second row, and the third vector across the third row. So a big list where this dimension is the number of points, and this is just your three coordinates, 0, 1, and 2. So I like to put the first vector on top, and the second vector, and the third sample vector, and so forth. So we can build a big matrix which just has all of our vectors in it. And then we can do processing on it later on if we want. Now, as I've written these are rows, right? They're going across the row. So since I'm column vector centric, I better remember those are transposed. And now if we look at the formula for R0 transpose, I have to transpose this thing. So it'll have my triplet of integers written as a row. Then I'll have to transpose this thing. Diag of S, fortunately, since it's a diagonal matrix, it is its own transpose, so nothing happens to that one. And then I've got R transpose sitting out here. So that would be M0. For R0, I would just have an M0 there. For R1, it's the same formula, but it's M1 times the same stuff. And so forth, going down like that. And then, of course, the final thing that you notice is, well, wait, look, each of these is post-multiplied by precisely the same combination. So I can factor that out of my matrix. So I'm just going to have a matrix here that contains only my triplets of integers. And then is post-multiplied by diag of S inverse times R transpose. So in sum, I get all my sample points in one very simple expression where if I call these triplets of integers M, the matrix M, make a matrix of all my triples, then I just multiply by diag S inverse times R transpose. And that will give me all my sample points. And that's basically your code for